I'm Matthew.
I'm Michelle.
I'm Minnie.
I'm Paige.
I'm Denise.
I'm Dan.
I'm Sarah.
And I'm Jessica.
Hi, I'm Minnie, an engineer working at the Navy base in Panama City. In today's episode of SciNotes, we will look at how geotechnical engineers use data from soil to design structures. Then, we will examine foundations and learn the differences between shallow and deep ones. We will test out foundation depths and see why one is more stable than the other. We will learn about expansion in structures and how these structures are designed to move, compensating for external forces such as heat. And then finally, we will learn about bridges, and specifically the joint and rigid members that make up the skeleton of a bridge. I'm so excited to dive into these awesome topics with you. Stay tuned for this episode of SciNotes, Civil Engineering. Let's imagine that a structural engineer designs a beautiful condo. It has the right materials, the right framing, the right everything. But what happens if the condo is built on land that consists of weak soil? It's up to geotechnical engineers to sample the soil on a construction site and design a foundation for the building so that it doesn't drastically sink once construction begins. Because of weathering, rocks at or near Earth's surface are either broken down into smaller pieces of rock or altered chemically to form new rocks. Weathering is a key process of the formation of soil, which is a combination of mineral and organic matter, air, and also water. Because of gaps in between the rocks, air and water fills the space between each particle of mineral and organic matter. It's the composition of soil, or the arrangement of mineral matter, organic matter, air, and water that leads to a site having either a naturally strong or weak foundation to build upon. That is why it's so important to study. Soil is classified in many ways, but the most common way is by grain size. Geotechnical engineers use soil profiles to determine the strength of the soil that they are building upon. Samples of soil are taken on site, analyzed in a lab, and then classified depending on their grain size, water content, and plasticity, or how easily shaped or molded something is. The grain size is determined by sieve analysis. Stacks of sieves are placed on a mechanical shaker, and the soil particles are sifted based on their grain size. Imagine the men and women who sifted through the Californian rivers during the gold rush. Sieve analysis is a very similar concept. We have an example of a sieve stack here, and we can see that in the base of each plate, there are different wire meshes, which collect the particles that pass through. Let's say that we have a soil sample from on-site. We can pour it into our top sieve, place the lid on top, and then give it a good shake. And naturally, the particles that are small enough will fall through. So as we can see, the gravel, which is the largest of the particle size, retained on the first sieve. Next, we had some saturated clay, which retained its shape, and so it was on the middle sieve. And then everything smaller fell through to the bottom pan. Once soil has been classified, geotechnical engineers will know how it will behave when a load is applied. To do this, it's also important for geotechnical engineers to find the depth of the groundwater table at the construction sites. The groundwater table is where soil becomes saturated. Above the groundwater table, soil is dry and acts differently from below the groundwater table, where all the soil is wet. Florida has a very low elevation, and the groundwater table is relatively close to the ground surface. Meanwhile, locations with higher elevation won't experience soil that's as saturated. The height of the groundwater table can also be affected by precipitation and how porous the soil is. Earlier we talked about how soil is classified by grain size. Another way to classify soil is by the drainage of water, which depends on how large the particles of soil are. Layers of gravel drain very quickly because there's room for water to pass through. We can see here that the particle size is very large. Sand is the next best soil for drainage. Sand's particle size is smaller, so it takes longer for water to pass through. Finally, we have silts and clays. Their particle size are so small that it naturally compacts, and there's not a lot of room for water to pass through. Different types of soils and foundations are found throughout the world. Soil is affected by many factors, such as precipitation, climate, and historical weathering. To continue to sustainably build structures, we must refine our understanding of soils and foundations. This infamous tower was first constructed in the 12th century and is a great example of a well-designed tower that was placed on poor foundation. The Leaning Tower of Pisa is what it came to be known as. Its original design included 8 stories, but the tower began to settle unevenly at an alarming rate once the 3rd story was completed. While eventually all 8 stories were built, it has taken serious mitigation efforts to keep the tower from leaning more. The original engineers did not account for the tower being built upon a shallow layer of saturated clay. It's because the site has a high groundwater table that the clay was saturated, and thus a poor location to build on. With a few weights and a foam foundation, we can model the importance of a strong soil profile and see why the Leaning Tower of Pisa got its name. So what I'm going to try to do is balance all 7 of these weights on the foam. And we can see that I'm lining it up as straight as I can. No matter how straight we built our tower, it eventually failed because it's not resting on a stable foundation, demonstrated here by the foam. The mechanism that accounts for this phenomena, at which a certain height the tower begins to lose its structural integrity, is called leaning instability. Because the Leaning Tower of Pisa became an infamous landmark, the citizens of Pisa, Italy, actually requested that the tower be stabilized, not standing straight up and down, but at an angle so that tourism could continue. After several efforts to stabilize the tower, some being successful and some only making the tilt worse, the structure was finally deemed safe and stable at a tilt of 3.99 degrees in the early 2000s. The foundations of skyscrapers and large structures can differ in many ways, but the main difference is whether beneath it is a shallow foundation or a deep foundation. These foundations are man-made and can support different types of weights and structures. Also, understanding the soil below, like we found out in the last segment, is very important in determining which foundation to use. Shallow foundations are designed to be only a few feet deep. They usually use footers under each column or wall to distribute the weight over a larger area. We can use a simple equation, P equals F over A, or pressure equals force divided by area, to illustrate why footers are so important for shallow foundations. As a force is applied to a foundation, sinking is expected, but it's important to keep settling uniform to avoid uneven settling, like with the Leaning Tower of Pisa. We can do a simple calculation to show how a larger foundation area decreases the overall pressure. So if a weight, let's say 1,500 pounds on a column with an area of 1 foot squared is applied without a footer, the pressure would be 1,500 pounds per square foot, or PSF. But if we add a footer to the bottom of the column that is 2 foot by 2 foot, or 4 foot squared, then the pressure would be 1,500 pounds divided by 4 foot squared, which is only 375 pounds per square foot. The pressure that the soil experiences is significantly reduced when a footer is added, which is important for shallow foundations. Shallow foundations are only practical for low-rise commercial or residential buildings that are generally lower in weight and can be supported by the compacted soil that it sits on. Deep foundations can be broken down into 2 categories, pile foundations and caisson foundations. We can learn what a caisson foundation is by understanding how it is constructed. To construct a caisson foundation, a deep hole is dug into the ground using an auger, which is a tool that is used to till soil from deep into the ground and bring it up onto the surface. You've seen augers in smaller scales, which are used for farming and for setting fence posts. You might even have one in your garage or shed, just like the one that I have here. The augers used for construction, however, can be driven 100 feet deep. A casing is also driven down into the ground so that additional soil doesn't cave into the hole that the auger is drilling. It's important that the soil retains its structure while the auger is in use. Once the hole is dug, concrete is poured into the hole. If additional strength is required, groups of reinforced steel bars, or rebar, can be placed in the hole prior to the concrete being poured. This is an example of rebar. The combination of reinforced steel and concrete is called reinforced concrete. It's commonly used for foundations and structures that undergo both compression and tension. The other deep foundation is piling foundations, which are made of pre-constructed piles. Rather than pouring the concrete on site, these piles, usually made of steel, are driven to the construction site and forced into the ground. Piling foundations are as simple as driving a stake into the ground with a hammer. You can see that the deeper that we go, the stronger that the stake becomes. Both deep and shallow foundations serve a great purpose in the civil engineering world, creating a platform to build purposeful structures, from the homes that we live in to the towering skyscrapers that define a city's skyline. In 2018, Hurricane Michael made landfall in Mexico Beach, Florida, and most of the homes were destroyed. News channels, however, began to report about one home that was left standing while everything else fell around it. The homeowners reported that their home was designed for the big one, and it exceeded the Florida Building Code. Building codes are a set of standards that all new construction must meet. They are a quality control measure for buildings and homes that are being designed. The building code for Florida says that engineers should design for wind speeds of 140 miles per hour. But this home in Mexico Beach was designed to withstand 240 mile per hour winds. Along with other increased design measures, this beach house had a foundation with piles that were 40 feet long. The average pile depth for beach houses is 20 to 25 feet long. With the addition of these 40-foot piling foundations, the house was able to withstand a high pressure and winds from Hurricane Michael, a Category 5 storm that presented sustained winds of 160 miles per hour. We've talked a lot about foundations so far, and you learned the difference between shallow and deep foundations. So let's do an exercise to show the difference between them. For this experiment, you will need a container that's approximately 1 foot by 1 foot by 1 foot. I'll be using this fish tank, and you can use the same, or even a cardboard box would work. You'll also need rocks or gravel, enough to fill the box about 1 inch deep. You'll need potting soil, enough to fill the box 8 inches deep. You'll need sand to fill the box 2.5 inches deep. A wooden block, it can be any size, but I'm using one that's approximately 2 inches by 2 inches. And it can be cut from a larger piece of wood or bought at a craft store like I did. You'll need wood glue and a wooden dowel with a diameter of about 1/2 inch. And it should be about 1 foot long. You'll also need weights. If you don't have any like I do, you can also use books and weigh them with a scale. Let's begin by preparing the soil in this order. The first layer of pebbles should be about 1 inch deep. The second layer is approximately 4 inches of potting soil. The third layer is 2 to 3 inches of sand. And then the final layer is another 4 inches of potting soil. Now let's construct the foundation model by gluing a dowel with the wooden block. The wooden dowel will serve as the pile for the foundation, and the block is supposed to be the floating foundation. To make things easier, if you don't have glue, you can also just drill in a hole. So now that we've built our foundation models, let's first test the shallow foundation. So by holding the dowel ends, place the wood directly on top of the soil. Next up, grab your weights or your books. You're going to start to pile on the weights onto the dowel. At first we see that it's pretty stable, but as we load more on, the shallow foundation starts to sink into the soil and also become unstable. The soil fails when it's pushed out of the sides and slightly up around the block. Let's record the weight at which the soil failed. We'll call this the failure weight at test 1. The weight for test 1 is 2 kilograms. We'll try another shallow foundation test. This time, we'll place the block deeper into the soil. So go ahead and dig back a little bit into that potting soil layer. We'll press it down firmly and then cover it back up with the potting soil. Next up, add your weights. I can already feel that it's much more stable, and we'll really be able to tell that this fails whenever the dowel starts to shake. And we can really see that it starts to lean whenever I've let go of the weights. And this is the point of failure. So for test number 2, we made it to 2.5 kilograms. Next, let's test a deep foundation, represented by the dowel. And specifically, this is an example of a piling foundation. So we're going to hold on to the block side of the wood and point the dowel towards the soil and slowly start to push it down. As we drive the dowel into the ground, it becomes more difficult as we reach a greater depth. If we push hard enough, the dowel actually reaches the bottom of the tank, and this represents bedrock in the earth. This will give the foundation more stability. Now let's load the foundation with our weights. We'll keep loading the foundation until it becomes too wobbly. So now we're up to 3 kilograms. Let's see if we can make it to 4. And 5 kilograms. And now at 5 kilograms, we can see that the foundation is wobbling a little bit, which is considered a failure. The point at which test 3 failed was at 5 kilograms. Now that we have our results, let's find the pressure experienced by the soil at the failure point for each test. For test 1, our failure weight was 2 kilograms. For the sake of consistency, let's go ahead and convert that from kilograms to pounds. So since there are 2.5 pounds per 1 kilogram, test 1's weight was 4.4 pounds. Test 2 had a weight of 2.5 kilograms, which equals 5.5 pounds. Finally, test 3 had a weight of 5 kilograms, which equals 11 pounds. Now that we have our 3 weights from our tests, we can calculate the various bearing pressure by using the weights we recorded at their points of failure and the area of the foundation that was used. The area for the shallow foundation will be the area of the wooden block. For my experiment, I used a block whose length was 3.5 inches and a width had 5 inches. So the area for this block was 17.5 inches squared. The area for the deep foundation will be pi times diameter over 2 squared. So the area of the dowel was 0.45 inches. So now that we have the max weights and the area for each test, let's go ahead and calculate the pressure for each test. Let's remember that pressure equals force divided by area. So the pressure for test 1, it was able to withstand 4.4 pounds of force over an area of 17.5 inches squared. That equals 0.25 pounds per square inch, or PSI. Test 2 was able to withstand 5.5 pounds over the same area of 17.5 inches squared. That equals 0.31 PSI. Finally, for test 3, we were able to load 11 pounds of weight over the area of 0.45 inches squared, which yields a pressure of 25 pounds per square inch. We can see that test 3 yielded the best results because the soil was able to withstand a higher pressure. We can see that through the data and also whenever we think about our deep foundations. The dowel was able to reach a much greater depth, which led to greater stability in the foundation. Buildings and bridges, and even roads, are designed to move, even if it's just a little bit. Let's think about the human body. We aren't completely rigid, are we?
No.
Engineers design a few things that are meant to move a lot. For example, pistons in an engine. But they also design for negligible movement. For example, in buildings. So what kind of negligible movements are we considering? Even though we consider buildings and bridges to be stationary, they are moving all the time. Structures can move due to wind or thermal expansion. Let's talk about thermal expansion. If you've taken chemistry, you might have learned that heat is proportional to the expansion of an object's volume. The formula for thermal expansion is delta L equals L naught alpha delta T. This means that the change in length of the material is equal to the material's original length multiplied by the material's coefficient of thermal expansion times the change in temperature. Roads in the northern parts of America are often subject to freeze-thaw cycles, which can lead to some epic potholes. Freeze-thaw cycles occur when materials, such as asphalt on the road, experience temperatures that rise above and fall below freezing temperatures over and over again. This constant state of expanding and contracting leads to cracking in the material. It's up to transportation engineers to mitigate these issues so that drivers are not subject to these potentially dangerous obstacles in the road. Even simple sidewalks, which constantly undergo a heating and cooling cycle, are designed with uniform breaks to decrease the chance of cracking. Let's consider a sidewalk that runs for 300 feet. The average high temperature for Florida is 91 degrees Fahrenheit, and the average low is 48 degrees Fahrenheit. We'll note that the coefficient for thermal expansion for concrete is 0.000006. That's 5 zeros. If we plug these numbers into our formula, the change in length of the sidewalk would be 0.077 feet, which is nearly a whole inch. That might not seem like a high number, but cracking will occur in the sidewalk if it spans for 300 feet. Expansion joints are purposefully put in sidewalks so that cracking will not happen so easily. Accounting for movement in structures that aren't designed to move is important. Thermal expansion, wind, and other factors force engineers to prepare for these small movements that could potentially collapse an entire building if they're not accounted for.
Hi, my name is Tim. I work for the Florida Department of Transportation as a civil engineer. My duty title is the Engineering Section Manager in our District Structures Maintenance Office. The most fun and unique aspect of my job is inspecting bridges that cross intercoastal waterways. In our department, we have divers because we not only inspect the top side of the superstructure of the bridge, we also inspect the foundation. We in Florida have a coastal environment, so we're very much looking for corrosion that happens due to the salt in the air and the salt in the water. And so we provide repairs for those defects or concerns to make sure that the bridges, they're maintained well and they're safe. The innovation in technology has drastically increased with just the fact that we have the computer software that we have nowadays to be able to run analysis and calculations very quickly to determine if a bridge is stable or if we need to do a repair. One of the projects I'm working on is dealing with ultra high performance concrete, commonly called UHPC. This innovative material has a strength that's 3 times more than what normal concrete is of 5,000 psi. It can get up to 20,000 psi depending upon how it's mixed. I got interested in civil engineering a little bit later in life, but I was always interested in science and math in high school, just how I could use those skills to make a difference in my community. If you're thinking about becoming a civil engineer, I would say find a person who is an engineer and just talk to them. Just ask them what they do. Shadow them if you can. Get them to show you a little bit of their day. I wished I could take you out on a boat with me to help you see how fun bridge inspection is and bridge maintenance is. But what I think is that after you find somebody to shadow, you really realize if that's your passion or not.
When structural engineers design buildings and bridges, they don't start with the windows, walls, and electrical fixtures. They break it down to the bare bones and start with the joints and members, or the skeleton of the structure. When it comes to bridges, in its simplest form, a bridge has 2 things: members, which act as the bones, and joints, where 2 members meet. An example of a member would be the beams that span across a bridge. There are many factors that go into selecting the right material for beams. Steel and concrete are the most used and are also frequently used together as reinforced concrete. Steel is the better material if the beam will be experiencing any type of tension. That's when forces pull on an object. Steel is very malleable, which means that it can be stretched and molded without breaking. If it is about to break, it will be obvious because of how much the steel has deformed. Meanwhile, concrete performs well under compression, or when a force pushes down on an object. Concrete is not malleable. It does not give an indicator, at least not just by looking at it, before it is crushed into many pieces when under too much pressure. Bridges can also be designed with truss patterns. In truss patterns, the beams are arranged in geometric patterns, usually triangles, to reduce the internal tension and compression that each member experiences. Here's an example of a crane with a truss design. The vertical, horizontal, and diagonal lines represent the members. Members connect at joints, and joints can be further broken down into 3 different types. The first type are fixed supports. Fixed supports are meant to join 2 members but not allow any movement, whether it's up, down, side to side, or rotation. Fixed supports can be surrounded by bolts, triangular plates, and welded to keep the structure from moving. The second type are pin supports, which are a step down from fixed supports when considering how much movement is allowed. Pin supports allow some rotational movement. While rotation is allowed at these locations, there should not be any movement from side to side. The third type are roller supports, which allow for the most movement. Roller supports, for example, might be used for a beam that should be able to move slightly from left to right, but not at all up and down. A great example of roller joints can be found in Panama City, Florida. The Hathaway Bridge, which was built in 2003, connects mainland Panama City to Panama City Beach. Thousands of people travel across this bridge every day. The Hathaway Bridge has installed roller joints to account for thermal expansion. With these roller joints in place, the road won't lift up or down, but it is allowed to expand and contract. Joints and members are crucial to structures, and we cross structures such as the Hathaway Bridge on a daily basis. Civil engineers must be able to account for so many variables, such as thermal expansion, wind, weight capacity, and even account for scenarios where traffic is backed up on the bridge, and non-moving weight sits on top of the bridge for an extended period of time. Civil engineering is a very broad subject matter. The continuous improvement of our communities and living standards wouldn't be possible without the hard work of civil engineers. Today we've seen how important it is to study what's both below and above the streets that we walk on. Pay attention when you're driving around your town. Now that you know a little more about civil engineering, can you appreciate all the work that's been put into designing and building your community? I'm Minnie, and I want to thank you again for tuning into SciNotes, Civil Engineering. Since we're so close to the beach, there's more sand. I don't need to say that. Stay tuned for this episode of SciNotes, Civil Engineering. That was weird. Wow.